So this heating and cooling stuff, heat transfer, if you've just got some object whose temperature is U and the surroundings have temperature U naught. And I want to emphasize this U naught doesn't mean the initial condition. This U naught just means the temperature of the surroundings. So U naught is some constant representing the temperature of the environment around the object. And then U is the temperature of the object right now.
Okay.
The differential equation we're dealing with is rate of change of temperature of the object is proportional to the difference in temperature. That is how different the object's temperature is from the surroundings right now. For example, if you have, if the object is very different in temperature from the surroundings, what would you expect to happen?
Like I guess thinking about the coffee problem, the coffee would approach whatever the room temperature would be.
As the eventual asymptote, yes. But what about like right at this instant? If the coffee is very, very hot and the air around it is very, very cold, what's happening right at that instant?
Well, I guess in a general sense, the air is getting warmer and the coffee's getting colder.
Right, in the sense that the heat is transferring from the hot object to the cold object.
Yes.
If the object is hot and the surroundings are cold, you're going to have heat transfer heat flow from the hot object to the cold object. And this actually has to do with the sign here. If we have U is a high temperature and U naught is a cold temperature, what sort of value do you get if you subtract a hot temperature minus a cold temperature?
You would still get a positive one.
Right. But we want the object to be getting colder in this case. So du dt, the rate of change in temperature, should be what sign?
Should be negative as because it wants to be colder.
Right. If the object's losing temperature, then du dt is negative. It's a decreasing, or u is a decreasing function. So we need this negative sign here to make these signs match up. That if u is a higher temperature, u minus u naught is positive. So we need a negative multiplier here to make the derivative have a negative value. As for the proportionality in the first place, what difference would you notice if you had let's say the coffee was much hotter than the surroundings versus if the coffee was just a little bit hotter than the surroundings? What difference would that make?
Like numerically or just visually? Or
either one.
I mean, the u of dt would be getting colder much faster.
Yeah, if you have...
Or the rate of change of cooling would be faster.
Sorry, what was that?
The rate of change of cooling would be faster if the object was much hotter.
Right, if these temperatures are very different, then the rate at which heat flows isn't going to be much faster. Heat flows proportionally to the difference in temperature. First of all, just in terms of direction, heat is going to flow towards the colder object. But also in terms of the rate, the more different the temperatures are, the faster heat is going to flow. And this is why we have this proportionality in the first place. The derivative of temperature with respect to time is proportional to the difference in temperature from location to location. And then K is just a constant of proportionality, which represents things like the mass of the object, the surface area, the material it's made of, any insulation, stuff like that, all just summed up as one constant of proportionality. So that's really what this equation represents. This is just saying the rate at which the object's temperature changes is proportional to the difference in temperature between the object and the surroundings. The constant of proportionality depends on the material properties of the object and the surroundings, and the negative sign is to get the signs to work out right, so that a hotter object will get colder versus a colder object will get hotter. Any questions on the setup of that equation so far? And then if we do actually want to solve this, what would we do? What is that separation of variables approach in this case?
So you would move the u minus u naught, you would divide it over, and then you would multiply both sides by dt.
Yeah, divide both sides by u minus u naught, multiply both sides by dt. So we're left with just 1 over u minus u naught du. equals negative constant proportionality dt.
Yes.
So at that point,
you would now integrate both sides.
Yeah. Now that we've separated the variables, we've got just u and du on one side, and just, well, there's no really t at all, just dt on the other side and a constant. We can now integrate both sides. And the left side is being integrated with respect to u, the right side is being integrated with respect to t. So what is the integral of 1 over u minus the constant?
We would have to do a u substitution for this, correct?
Or since we're already using u, let's say a v substitution.
Sure.
Let's say, what would be a good choice for v here?
U minus u naught.
Yeah. V is u minus u naught. That way we just get 1 over v, which is going to be much easier to deal with. And since v is just 1u minus a constant, what's dv going to equal?
Just 1 du.
Yeah. Which means we can freely substitute. Du can just be replaced with dv. So we get integral of 1 over, this whole thing is going to be v, dv. And then on the other side, of course, we still just have, actually, we could pull out negative k as a constant.
Can we just make it negative k? So what can we implement in class? We did, when we ever have a constant, we just like combined it and then said what it was. So like simply integrating negative k dt yields negative k t plus c.
Yeah.
Okay, never mind.
Yeah, that works. I usually think of it in terms of pull out the constant, you're left with just integral of 1 dt, which is just t.
I see, okay.
So you could also think of it as integrating that constant. Either way it works.
Okay, so I'm just gonna call the c attached to the negative kt, I'm gonna call that c2, and then the integral of 1 over v is just ln of v.
Right.
And then v being u minus u naught.
Yeah, so we can fill that in, logarithm of u minus u naught. And strictly speaking, we would have a plus c on this side as well.
Yes, plus c1.
But since we have a plus a constant on both sides, we could subtract the c1 from both sides, because we ultimately want to solve for u anyway. And what is an arbitrary constant minus another arbitrary constant?
Just a constant. So we'll call that, so we'll just say c3 is c2 minus c1.
Yeah, or let's just call that c.
Okay. Since
there's only one arbitrary constant here anyway. And also k and u naught, but those actually represent physical properties of the system. The temperature of the surroundings and something about how quickly heat can flow through this barrier. And then what else would we need to do to isolate u here?
You take the e of both sides.
Yeah, or I would say exponentially both sides, raise e to the power of both sides.
Right.
And then on the left side, exponential and logarithmic functions cancel out. So we get just u minus the initial surrounding temperature equals, and then over here, we've got e to the power of something plus something. How can we split that up?
Using exponent rules, you just do e to the negative kt times e to the c.
Yeah. So we got e to the negative kt. And also, since c is just an arbitrary constant, e to the c is another arbitrary constant. So let's just call that, let's say, capital C.
Sure.
So there's almost to our general solution. We still need to isolate u. So let's go ahead and add u naught to both sides as well. So this would be our general solution, in the sense that all solutions of the original differential equation will have this format. Something times e to the negative kt plus the surrounding temperature. Any questions on that process so far? And then if we want to examine the behavior of that, what's going to happen? Usually what we most care about is what happens after a long time. And then we can fill in details of what happened earlier as well. But if we just look at what happens after a long time, that is, formally we're taking the limit as t approaches infinity of u. What's going to happen to this term, this exponential function, as t gets larger and larger?
I believe u will approach c plus u naught.
What happens to e to the negative kt though? If you raise e to a more and more negative power, what's going to happen?
Oh, it's going to approach u naught, excuse me.
Yeah. this term goes to 0 because e to a more and more negative power gets smaller and smaller, closer to 0. So this term, the whole thing becomes 0, and we're left with just the temperature of the surroundings. And that's what we should expect, right? Physically, we would expect the hot coffee to cool off, approaching the temperature of the air around it, assuming, of course, that the air itself is not changing temperature. Realistically, the air will get a little bit warmer, but we're assuming that this coffee is in a very large room. So there's lots of air, and the air doesn't change temperature very much. So this at least matches the end behavior we should expect. That if you were to make a graph of time versus temperature, U0 is going to be an asymptote, and all of the solutions are going to be exponential decay functions approaching U0, approaching the temperature of the atmosphere. And of course, if the coffee starts off already at room temperature, it's just going to stay there. That's an equilibrium solution. We can actually figure that out, the equilibrium solution, just by going back to the original differential equation. If we want to find the equilibrium solution, we don't even need to solve the equation itself. Because for equilibrium, if we're trying to find what's a value where if it's at that value, it stays at that value, what's the derivative of a function that doesn't change?
Like a constant?
Yeah, if we assume the function is a constant, then what's its derivative?
0.
Exactly, it should be 0. So if you want to find the equilibrium solution, assume that the derivative happens to be 0. If we can find a u value that makes the derivative equal to 0, then that means that u value is a constant solution. So we can set that up. Just replace du dt with 0. And do we have any u values that would make this whole thing 0?
Positive 10, because we know u0's 10.
Yeah, or more generally u0, whatever u0 happens to be.
Sure, right.
It still has 10. But again, I would usually recommend solving it in terms of these parameters as unknown constants, and then fill in the values later if you need to. Because this way we get a more general idea of what's going on with any heat flow problem, not just one where the atmosphere happens to be at 10 degrees. So in general, we're going to get u equals u0. And note that this is a constant value. If we had gotten something that's not a constant, then that means there is no equilibrium solution. But the fact that we get u equals a constant, that matches up with the idea that the derivative is 0. That is our equilibrium solution. And in more complicated differential equations, you might get several equilibrium solutions. In this case, we just get one. And that tells us that if the temperature of the object is already u0, the temperature of the surroundings, then it just stays there forever, which is what we should expect anyway.
Right.
But then the other solutions are typically either going to be approaching the asymptote or diverging away from that asymptote. In this case, everything's approaching that asymptote. So we say this is a stable equilibrium. Whereas unstable equilibrium would be if everything nearby is diverging away from the asymptote. Any questions on the behavior of that so far? Now, what if we wanted to get a specific solution? If we wanted to know, like we know that there's many curves that match this differential equation that have this behavior. What if we wanted to narrow it down to one specific curve? What other information do we need?
Can you repeat the question? Sorry.
If we wanted to narrow it down to just one specific solution, like let's say instead of having a family of solutions, instead of having this whole general solution, suppose we wanted to narrow it down to one specific solution that's actually going to happen. Because if you just have coffee cooling off, it's not following all these different curves. It's only following one of those curves.
Right. We would need to know the initial temperature of the coffee.
Yeah. Yes, you do need to know K. But the thing is, the K value could be found. The K value is for all of these curves. So to find the K value, you would have to have some more information. Maybe you need to know several points on the curve. Or maybe you need to know something about the material properties of the object and its surroundings. But let's say we already know the value of K, and we already know the value of the surrounding temperature. If we wanted to find the value of C, we just need the initial conditions. We need usually the temperature at time 0, but really the temperature at any time. So let's say we know the temperature at time 0.
And we do in this case, right? It's 10.
10 wasn't the temperature of the coffee, though. 10 was the temperature of the surroundings.
Oh, I see. Wait. U0's the temperature of the surrounding, so therefore U of 0 is, okay, got it.
And the notation is kind of confusing here.
Yeah.
We usually do use y sub 0 or whatever to mean the value at time 0. But in this particular problem, U sub 0 means the temperature of the surroundings, not the temperature of the object at time 0. So let's use another variable. Let's say U sub I be the initial temperature. So U sub I is the initial temperature, the temperature when time is 0. And let's say we already know the values of K and U sub 0, the surrounding temperature. Then we could fill that in. We could say, substitute in 0 for T and initial temperature for U into our general solution. So if we fill that in, U gets replaced by U sub I. T gets replaced by 0. So we get C times e to the 0 plus the surrounding temperature. And what's e to the 0?
1.
Yeah, so we just get C times 1. And then if we solve that for C, what do we get?
Ui minus U0.
Right. The initial temperature of the object minus the temperature of the surroundings. In other words, the difference, the initial difference between the object's temperature and the surroundings temperature. So we can now fill that in for C, and we get, as a specific solution, U equals that difference, Ui minus U0. That is the initial difference in temperature times C e to the negative KT plus U0. So this would be what we call the specific solution.
And that's U of T.
Yeah.
So that's U of T. And then in this case, the U0 would be equivalent to 10.
Right. Yeah,
so it was, okay.
This is the temperature of the surroundings, which in this case is 10. U sub I would be the starting temperature, the initial temperature of the object itself.
And that would, in our scenario, that's just U.
It would be U of 0.
Okay.
So we could write that as U of 0, not to be confused with U sub 0, which means the starting the temperature of the surroundings.
All right, and then okay. There's no C there though, correct? Or
yeah, that is the C value. Sorry about that. So this is the C value times e to the negative KT.
Okay.
Plus the asymptote, the surroundings temperature. And then if actually based on that information, we could find the K value. To find the K value, we need one more data point. So let's say we know the initial temperature, and we also know that, let's say, 100 seconds later, it's at a certain new temperature. You could fill in 100 for T and the temperature after 100 seconds, or whatever the time units are. And then at that point, K would be the only unknown left. If we know the starting temperature, and we know the temperature of the surroundings, and we know that at a certain time, it becomes now a certain later temperature, then K would be the only unknown left. So you could solve for K, ultimately using a logarithm.
Okay, so we created a new variable for the initial temperature of the object. That just wasn't given to us in this question.
Right.
I see.
You could just write it as U of 0, like this format. So that would be not so much U. I mean, it is technically a new constant in the sense that it's a numerical value that's not really provided.
Right, but as long as we specify that U of I is the initial temperature of the object, then it's something that is like forward as in like, okay, like this makes sense in terms of your
and
formula.
Of course, when you introduce a new symbol like that, it's a good idea to explain what you mean by that symbol.
Okay.
That this is the initial temperature. And this kind of is sort of a general solution in the sense that U sub I could be any value. But I think I would call it a specific solution in the sense that it tells you, instead of just saying, we've got some arbitrary unknown constant C, we now know what that arbitrary constant actually means. It's no longer really arbitrary. It really just means the initial difference in temperature. So it now has a physical meaning.
Got it.
Any other questions on that one?
I have a question.
Yeah, go ahead.
Would you say then that u of 0, when u of 0 is less than u naught, that like the curve u of t will increase approaching to u naught?
Exactly. And we can see that both from the graph. Like if you start with an initial temperature that's lower than equilibrium, then we're going to get a function that increases towards equilibrium.
Got
and
it.
also we can see that from the original differential equation. If u is smaller than u naught, what is this value going to be?
Negative.
Right. Multiply by negative k, and we get a positive value for the derivative. So that also suggests an increasing function.
Got it. Okay, thank you.
I think we can even see that from the specific solution, that if u initial is smaller than u naught, this is going to be negative. A negative multiplier times e to the negative kt means an upside down exponential decay. So it's going to be decaying upwards towards the asymptote. So you can often get the same information from the original differential equation, graphs of it, either using the general solution or a direction field, and from the general or specific solution. So it's often a very good idea to, like if you want to find out some information about some physical situation, consider what you would expect from the physical situation itself based on your own everyday experience. And what does the differential equation tell you? And what do the general and specific solutions tell you? And what does a graph or a direction field tell you? And if all of those agree, if all of those give you the same information, that's a very strong sign that yes, this really is correct.
Okay. Sorry, the nomenclature still is confusing to me with the sub-zero and the big zero. So u of 0 equaling 10 means that the area around the coffee would have a temperature of 10.
Well, u of 0 is not 10. The 10 in this problem was u sub 0. So let me mark this just to make it more clear. In this problem, u sub 0 means the temperature of the surroundings.
Okay.
As opposed to u of 0 in function notation. U of 0 means the temperature. So let me change that. U of t means the temperature of the object.
Okay, and then why did we at time t? Okay, then why did we use u of I to reference the object?
Well, you could also use, you could call this u of 0.
Okay.
I was just also calling it u sub I to represent the initial temperature.
Okay. So you could call that u of 0. So wouldn't that just be 10 minus 10? Or no, that's 10 minus u naught.
Other way around, u of 0 minus 10. I think this problem was saying that the
u of 0 minus 10. U of 0 is 10 because it says suppose that u of 0 equals 10, solve for u of t.
Was it saying the object's initial temperature is 10, or was it saying the surrounding temperature is 10?
It's saying u0. It's saying what you're writing right now, that u0 is 10. So the initial temperature of the object is 10.
U of 0 or u sub 0?
The third one.
This one.
Yes.
Okay, so if u of 0 is 10, that's what you'd fill in here.
Okay.
But if we don't know the surrounding temperature either, then we can't really say much about whether it's increasing or decreasing.
I see.
Because the important thing in terms of whether it's decreasing towards an asymptote or increasing towards an asymptote, that's all about is the initial temperature of the object hotter or colder than the temperature of the surroundings.
I got it. Okay. Thank you. Yeah, sorry, the nomenclature is a little confusing to me because...
Yeah, they really shouldn't be using u sub 0 to mean anything other than the value of u at 0.
Yeah, thank you for clarifying that.
Any other questions on that one? Or yeah, I'm recording these. I'll post them, post links to them on the website, math.ncheese.org later. Any other questions on separation of variables or the heating and cooling stuff in general? or any other topics you'd like to work on?
I have a question, and it's a pretty dumb one. I don't understand how to read the basically limit, or as like something approaches a certain value.
Mm-hmm.
I don't know how to read it for directional fields.
You mean finding the limit from a direction field?
Yeah.
Well, let's try that out. Because direction fields are a very good way to get an idea of what's happening with the differential equation, even if it's not one you can solve. Do you want to look into how to draw the direction field in the first place, or just how to interpret it once you've got it?
How just to interpret it?
Okay, then let me use some computer software for drawing it real quick. And anyone have any suggestions for what differential equation you want to try out on the direction field? Or should I just make
Sure. How about you use dy over dt equals y plus 3?
Y plus 3?
Yeah.
Okay. Fill that in. And is this visible?
Yeah.
Okay. All right, so if we wanted to graph direction field for y prime equals y plus 3. Type that in, hit graph. Probably want to narrow that down a little bit. Let's say we got t from 0 to 10, y from maybe -5 to 5. There we go. So here's our direction field. And from this, maybe we should narrow. It looks like what's probably the most important y value to consider here? Where is something really important happening?
At -3?
Yeah, it looks like something very important is happening at -3. For one thing, we can see that everything above -3 is an increasing function. Everything below -3 is a decreasing function. And we can also even see that from the original differential equation itself. If y prime equals y plus 3, once again, how do we find an equilibrium solution from the differential equation itself?
You set it equal to 0?
Yeah, specifically, we fill in 0 for y prime. So if we say, let y prime equal 0, in the sense that we want to find what has to happen to make the rate of change 0, to make it no change at all, then we get 0 equals y plus 3, so y has to be -3. So algebraically, we can see that y equals -3 is where we would expect an equilibrium solution. In other words, when y is -3, we should expect a constant solution. So one of the solutions is just going to be constant at y equals -3. What if the starting value, the initial value, is a little bit more than -3? What would we expect to happen if we started off at, let's say, -2? Based on the direction field, what's happening to the function at that point?
It's increasing?
Yeah. In fact, the arrow here, that arrow tells us what's the slope at that point. So we've got this slope, but then a little bit later, the arrows are now steeper. So we should expect a steeper slope and steeper and steeper and steeper, essentially following parallel to the nearest direction field lines. Whereas if we were to start closer to -3, we've got a flatter slope, but it's still going to get steeper and steeper and steeper because we're getting towards arrows that are steeper, larger slope. Likewise, if we start below -3, what do you notice about the direction field arrow there?
It'll be decreasing.
Yeah, we've got a decreasing function because in this region, the arrows are pointing down and to the right. So we go down and to the right, and then it looks like that's getting steeper and steeper as well because we get two arrows that have a greater slope. So just based on these few sample solutions, usually called integral curves. Integral curves just means graphs of sample solutions that we put on the direction field. It looks like y equals -3 is the one and only constant solution. Everything else is going to be, looks like exponential decay diverging away from that equilibrium solution. So just based on those few examples, it looks like we can say that all the solutions with initial value above -3 are going to diverge to positive infinity. Anything with an initial value below -3 diverges to negative infinity.
Excuse me, I have a question.
Yeah, go ahead.
In the top left, so this is, I asked you to do this integral curve because I believe it's a solution for problem 2, but I didn't know how to verify or explain my answer besides using the way you use in the top left, but I felt that wasn't very complete because simply that saying that, oh, if you set dy over dt to 0, which would be like the solution it would approach, then y being -3 would be the correct answer. And the only way to have that would be for it to be y plus 3. Is that a sufficient solution to the problem? I feel like that's not the way he wanted us to do it.
Well, that does provide a function or a differential equation that has -3 as an equilibrium solution.
Yes.
And of course, it's not the only one that has -3 as an equilibrium solution, but it is a differential equation that has -3 as an equilibrium solution.
As t approaches infinity, yes.
Right. Well, actually, in this case, what happens to all the other solutions as t approaches infinity?
Well, they either go towards positive or negative infinity, depending on whether they're above or below -3.
In other words, they're diverging away from -3 instead of converging towards it. So we would call -3 an unstable equilibrium here.
Okay, but as t approaches infinity, it would approach y equals -3, correct?
No, all of these other ones are approaching positive or negative infinity.
But as you move farther along t, it approaches y equals -3, no?
Are you talking about to the right or to the left?
To the right, as that's positive infinity. Negative infinity is not the concern for me.
Well, as we go towards positive infinity, it looks like all these curves are diverging away from -3. In fact, this one actually allows you to just click on an initial value and it'll show you the curve. So all these curves are diverging away from -3, not towards it.
Real? Am I interpreting the graph wrong then? Because at the very right-hand side of the graph, doesn't it look like the arrows are getting less steep in slope, which means that they're converging towards -3?
They're still pushing the solution away from -3 though.
I see.
Like if you start off at, let's say you start off at time 10 and y equals -2. The arrows here are saying go away from -3. Or if you start off at time 1000 and y equals -4, those arrows are still pushing you further away from -3. So this is unstable equilibrium. All the other solutions are diverging away, not towards.
I see. Okay.
If we wanted to change that though, how do you think we might be able to modify the original differential equation so that everything's approaching towards -3 instead of diverging away from it? If we still want to have -3 be an equilibrium solution, what else other than y plus 3? Sorry, what was that?
I'm sorry, I cut you off, but you just make it negative? Both
Yeah, let's try making it negative. If we change this to y prime equals -y minus 3, that still has -3 as an equilibrium solution. If you plug in -3 for y, this thing still resolved to y prime equals 0. But let's see what happens if we make that modification. If we change this to y prime equals negative y minus 3. What do you notice about the arrows here?
I see. Now they're all moving towards negative
Right.
3.
So we still have negative 3 as an equilibrium solution, but all the other solutions, no matter what the initial value is, these are all approaching negative 3. So we would say this is stable equilibrium at y equals negative 3.
I see. And the reason why, because how come making it a negative y was the reason that it then shifted it to a stable equilibrium?
Well, let's take a look at what's happening above and below. I'm going to introduce an idea called a phase line. Has that come up in class yet?
It doesn't sound familiar to me.
It's probably going to show up a few seconds later when you get to autonomous equations. The idea is if you're talking about, this equation is what's called autonomous, meaning that y prime equals something about y only. There's no time dependence. There's no t in this side of the differential equation. The idea here is that if you take a look at, let me clear out the integral curves here. If you take a look at, let's say, a single cross section of the direction field here, like just this cross section, notice that we've got a certain pattern of what the arrows are. If we take a look a little further forward in time and look at this vertical cross section, or a little further forward in time and look at this vertical cross section, what do you notice about those cross sections?
Aren't they all the same?
Yeah, they're all the same because the original differential equation is time independent. It doesn't matter what time it is. The only thing that matters for the slope is what's the y value right now. So time doesn't matter. We don't really need the whole direction field. We can just take one single cross section. And that's really what a phase line is. A phase line is essentially a single column, a single one-dimensional cross section, a vertical cross section, essentially just looking at the y values. And what did we already notice is the most important y value here?
Negative 3.
Yeah, we know that negative 3 is the equilibrium solution. So let's put a mark at negative 3. So marking that, negative 3. And we know that's equilibrium. We know that if y happens to be negative 3, because this phase line is essentially a y-axis, if y happens to be negative 3, then the slope is going to be 0. I'm just going to mark a dot there to show that this is equilibrium. And we'll label that as equilibrium. But if we take a look above and below, let's say you take some y value above negative 3. Doesn't really matter which one. Let's say just 0 for simplicity. If you plug in 0 for y, what do you get for y prime?
You would get negative 3. So the slope at 0 would be negative 3.
Right. And more generally, if y is greater than negative 3, then y prime is going to be what sort of value?
Say that one more time, sorry.
If y is greater than negative 3, if you plug in any value for y that's above negative 3, what sort of value do you get as a result for y prime?
A positive slope? Rather negative slope. Excuse me.
Yeah, you're going to get negative because we're plugging in a larger value for y, but then we're making it negative or taking the opposite. So in general, if you plug in any value greater than negative 3 for y, then the resulting y prime is going to be negative. In other words, we get a negative slope.
Yes.
So any function that has an initial condition above negative 3 is going to be a decreasing function. So I'm just going to put a down arrow here. On the other hand, what if we plug in a value for y that's lower than negative 3? Like if you plug in negative 1,000,000 for y.
It would be a positive slope.
Yeah. If y is less than negative 3, and we can interpret that as the initial condition. It's really if any point on the graph is less than negative 3, then y prime is going to be positive. So it'll be at a positive slope, an increasing function. So I'll draw an up arrow here. So this diagram, this phase line, means that if y is -3, then it's steady. It'll just stay there forever. But anything above -3 gets pushed down towards -3, such as all of these curves. And anything below -3 gets pushed up towards -3. So without even the direction field, just based on this phase line, what kind of equilibrium is this?
It's stable because it's always going to be at -3 at that point.
Right, or more specifically, everything nearby is pushing towards -3. Equilibrium is the fact that if it's at -3, it'll stay there. Stable is talking about all the points nearby. Everything nearby converges towards that point. Whereas unstable would be if the arrows were pointing away from it, if everything nearby was diverging away from that point. So this phase line can be a very useful way of interpreting or what kind of equilibrium it is, where the equilibrium is, what kinds they are, and the overall end behavior without even drawing a full direction field. You're essentially just looking at a single cross-section of the direction field. Essentially, we're looking at this cross-section. That at -3, the slope is 0. Anything above -3 has a negative slope. Anything below -3 has a positive slope. So we really are just looking at that single cross-section of the direction field as all we really care about. That gives us all the information we need. Any other questions on the direction field stuff? And one other quick example, just to get an idea of what else can happen here. Let's say we have something like y prime equals y times y plus 5 times, let's say y minus 5, just to make it positive, times y minus 9 squared. And let me make that a little bigger. Let's say y goes from 0 to, let's say, -1. Now let's make it -2 to 15. Before I even hit graph, what would you expect the equilibrium values to be here?
5 and 9.
5 and 9, and also what else? What else will make this whole thing 0?
0.
Yeah, so if y is 0, or if y is 5, or if y is 9, those would all be equilibrium values. And that might be a little difficult to see what's going on. Yeah, that'll work. So if we start off at 0, we get a flat line. If we start off at 5, if we start off exactly at 5, that'll be a flat line. If we start off exactly at 9, it's a flat line. But if you take a look at what's going on elsewhere, the type of equilibrium starts to emerge. It looks like if you're exactly at 9, you stay there forever. So 9 is equilibrium. What if you're a little bit below 9? What's happening?
It looks like you're just, if you're only a little bit below 9, you're still approaching 9.
Right. What if you're a little bit above 9?
Then you're approaching infinity, it looks like.
Right. So from below, 9 seems stable. From above, 9 seems unstable. And the term for that is semi-stable. Y equals 9 is semi-stable equilibrium, in the sense that it looks stable from one side and unstable from the other side. What about at y equals 5? What's going on near 5?
It also looks semi-stable.
What's happening above versus what's happening below?
Oh, it's unstable. Never mind.
Yeah. If you have anything just a little bit above 5, it diverges upwards away from 5. Anything a little bit below 5 diverges downwards away from 5. So the phase line near there would be upwards above and downwards below. So that would be unstable. So y equals 5 is unstable equilibrium. And as for 0, if we try some values above and some values below, it looks like everything near 0 is approaching 0. We've got values above 0 that are going downwards towards 0, values below 0 that are going upwards towards 0. So what do we have at y equals 0?
That'd be a stable equilibrium.
Yeah. So this direction field exhibits all three behaviors. We got stable equilibrium at y equals 0, unstable equilibrium at y equals 5, and semi-stable at y equals 9. So we can categorize the end behavior based on initial conditions. It looks like anywhere between 5 all the way down to negative infinity, all those initial conditions converge towards 0. Whereas anything from 5 to 9, anything between those are all converging towards 9. And then anything above 9, those are all diverging off to positive infinity. So there's really three types of end behavior here: converging towards 9, converging towards 0, diverging towards positive infinity. And we can categorize those behaviors based on the initial conditions, whether we have initial conditions in the range from negative infinity to 5, or from 5 to 9, or from 9 to infinity. Any other questions on that? And if you want to learn more about this subject, take a look in the textbook for the terms autonomous equation and PhaseLine. Those would be the main terms to look for if you want to see more about this. So try this out with some more examples. You can make direction fields of any first order differential equation as long as you can write it as y prime equals anything. So try that out, graph some direction fields, and see if you can interpret what's going on here based on the direction field. Give that a try, and I will see you next time.